Hello and welcome to another lecture of Physics 305 Electromagnetic Field and Waves. This is lecture 21, and if we just briefly review what we did last time, then last time we basically derived in quite a lot of detail the Fresnel equations for TM polarized electromagnetic waves. Now, what this basically meant was that so Tm basically meant that the magnetic field, that B is perpendicular to the plane of incidence. So that means that E is inside the plane of incidence. And the case that we basically did was a more general case where if this is the interface between a material with the refractive index n is equal to 1 and refractive index n is equal to 2, then if this is your surface normal and this is your incoming wave vector, this is your outgoing wave vector, this is your angle of incidence, this is your angle of reflection, and this is your angle of transmission, then if this is your incident k vector, this is your reflected k vector, and this is your transmitted k vector. And k vector is the propagation vector. This determines the direction of propagation, and it's equal to 2 pi by lambda, where lambda is the wavelength of the electromagnetic radiation. And we said that E is in the plane of the of incidence because it's TM polarization. So let's say E points somewhere like this. This is E incident. E reflected would then point somewhere like this, and E transmitted would point somewhere like this, right? And of course, let's just make sure we know what axes we were talking about. So we took propagation along the z-axis, nothing special along z. We took x to be within the plane of the paper, and we took y to be outside the plane of the page. So basically, this is the geometry we analyzed. This, of course, is oblique incidence. So we did oblique incidence. Of course, we did normal incidence, I believe, in lecture 19, which was a special case of this. And then basically what we found was that given this scenario, we found that that E naught reflected is equal to some factor alpha minus beta over that factor alpha plus beta times E naught incident. And similarly, we found that E naught transmitted is equal to 2 over alpha plus beta times E naught incident. What was alpha? Alpha we saw was equal to the cosine of the angle of transmission over cosine of the angle of incidence. And this factor beta was equal to mu1 n2 over mu2 n1. And now for most materials, actually for most dielectrics, but not all, but most dielectrics, this is actually almost equal to n2 over n1, because for most dielectrics, mu1 is approximately equal to mu2, but not all of this. You have certain magnetic materials where this is not the case. So these are our deflection and transmission coefficients. But one very interesting thing was when, and we explored this a bit in the homework problems also, was that when alpha becomes equal to beta, then E naught R becomes equal to 0. You see, and what's the free parameter here? The refractive indices are constants. N2 and N1 are for a given electromagnetic wave, they're a constant. The only thing you can change, of course, is the incident angle. Right? The only thing you can change is the incident angle. So you change your incident angle, and then and you change alpha, and beta is of course still a constant, and corresponding to every theta I, you get a corresponding theta t, and at some point alpha can become equal to beta, and so the special angle, so the angle for which alpha becomes equal to beta is called the Brewster angle. It's called the Brewster angle, and this is a very nice concept. So the Brewster angle basically takes place when the cosine of theta t over the cosine of theta I becomes equal to n2 over n1. You can actually simplify this quite a bit, and if you do that, you can basically show that n2 over n1 is basically equal to tan of theta b, where theta b is the Brewster angle, but it of course is the angle of incidence. So what it tells you is that if you have TM polarized electromagnetic radiation, and if it's incident at the interface between any two dielectrics, then if you can make the angles of incidence such that the angle of incidence is equal to the Brewster angle, then you get no reflected light and all the light is transmitted. So you can imagine that this has a lot of applications in both optics as well as common everyday objects like sunglasses, where we can actually polarize the light that's actually reflecting from a certain interface, and then that allows us to engineer it for a particular application. So I hope that this is clear. And basically this pretty much there's one thing I guess that I can mention, which is that you can once again define the total reflectivity, which is equal to the reflected intensity over the incident intensity, and you can define the transmissivity, which is equal to the transmitted intensity over the incident intensity, right, as it did for a normal interface. And you can show that R plus I is equal to R plus T is equal to 1 always, right, for conservation of energy. So this pretty much wraps up everything we wanted to do for a dielectric interface. We've looked at energy transfer. We've looked at oblique and normal incidence. We've looked at the Brewster angle, so on and so forth. The next conceptual thing that we want to do, so this is an altogether new topic in some sense, is so I'll just put this so that we know that we're finished here. So the next topic that we have to do is electromagnetic waves in a conducting material and at a conducting interface. So the relevant Maxwell equations the relevant Maxwell equations inside a conductor would of course be that the divergence of the displacement is equal to the free charge. Take care, we'll call this equation 1. Then equation 2 would be that the divergence of the B field is equal to 0. The third Maxwell equation is that del cross E is equal to minus the partial derivative of B with regards to T. And the fourth Maxwell equation basically is that del cross H is equal to the free current. So it's that del cross H is equal to J free plus partial D by partial T. So these are our Maxwell equations which we got from our chapter on electrodynamics. Now what we'll do is that we'll simplify them a bit, and I'll write the simplified forms on the next page. So basically, instead of del dot D, I can write del dot E is equal to rho F over epsilon, and instead of del cross H, I know that H is equal to basically B over mu, where mu is the total permeability. So I can basically write that del cross B is equal to mu times JF plus mu partial D by partial T. So if I write down an equivalent form of the Maxwell equations, I'd be very pedantic about this because this is the starting point. So I just want to make sure that we all agree on the starting point and we understand what we're talking about. So the equivalent form would be that del dot E is equal to the total free charge now over epsilon. This is equation 1. Equation 2 would be that it's still the same, that del dot B is equal to 0. Equation 3 becomes del cross E is minus partial B by partial T, and equation 4 becomes that del cross B is equal to mu times the free current plus mu epsilon times partial E by partial T. And let's just make sure we're careful about our vectors. Now this term JF, this is the free current, and one thing we know about the free current, if you remember, was that we looked at Ohm's law, one form of it, and it basically told us that, so we extrapolated from it that JF was equal to something called the conductivity times the applied electric field. We did this when we were doing in electrodynamics, where sigma is the conductivity. So if that's okay, then I can express equation 4 as, so I can express this equation as, so equation 4 then becomes del cross B mu E plus mu epsilon partial E by partial T. Okay, and I hope you all understand where all these terms are coming from. Now if that's okay, so then these are our 4 Maxwell equations. So if it's a bit messy, but please make sure that you understand exactly what equation 1 means, exactly what equation 2 means, exactly what equation 3 means, and of course this is the equation 4 that we'll be using. The key point here is that, for example, in equation 1 we have the free charge over epsilon, not epsilon naught. That's because all the polarization effects are inside there, because we started from del dot D is equal to the free charge. Similarly, for the magnetic field, all the bound currents and so on and so forth, it's already inside this factor of mu here, because we started with del cross H. So this is very important, how all of that physics is already in, a lot of the physics is actually encapsulated within these Maxwell equations. Now let's go back to something we did at the very start, which was the continuity equation. Now the continuity equation was basically a statement about the conservation of charge. And the continuity equation basically was that del dot current density is equal to minus of the partial derivative of partial rho by partial t. ठीक है, तो and this is true at every given point, right? This is true at all points. So if you substitute jf is equal to sigma e in the continuity equation, what we get is that del dot sigma e, so where sigma is the conductivity, is equal to minus rho f by partial t. ठीक है, लेकिन we know that this is equal to sigma times, so del dot e is rho over epsilon, right? So this is then we've already done this is rho over epsilon. ठीक है, so what you have is you have a differential equation. What's the differential equation? Well, it's what you have is that partial rho f by partial t is equal to minus sigma over epsilon times partial f, right? So if we solve this, what we get is that the natural log of rho f is equal to minus sigma over epsilon times the time plus c, and so rho f becomes equal to some constant c times e to the minus of sigma over epsilon times t, right? And if you plug in initial conditions, basically if you plug in say t is equal to 0, then what you find is that c is equal to the free charge density at time 0, okay, because there's of course some time dependence here. So the free charge density as a function of time is equal to, and this is just following from the continuity equation, is equal to the free charge density at time t is equal to 0 times e to the minus sigma over epsilon times the time. Okay, and so basically what this tells us is that this initial charge density because of the continuity equation, this initial charge density at a point decays exponentially, and so at any other point the new charge density at that point is the initial charge density multiplied by an exponential factor. Okay, and so in time tau, which is equal to epsilon over sigma, okay, we have e to the minus sigma over epsilon dotted with time, and that time is epsilon over sigma, so this becomes equal to e to the power minus 1. So in time t is equal to epsilon over sigma, p of t, which is equal to epsilon over sigma, becomes equal to p at 0 over e. Okay, so you get a 1 over e decay in time epsilon over sigma. So we define tau to be equal to epsilon over sigma, and this time for every particular material is called the characteristic time. It's a material dependent property because it depends on the conductivity and the permittivity of the material. Okay, now notice that if sigma is infinity, yani ki you have a perfect conductor, right, then tau is equal to 0. And if sigma is equal to 0, yani कि you have a perfect insulator, then tau is equal to infinity. What that means is that if you have a conductor, then any free charge you put somewhere is dispersed very very quickly and neutralized. As we always say, you don't have any net charge at any point inside a metal conductor, and this is why. And for the same reason, then, if you put a net charge, some charge somewhere in an insulator, you expect it to stay there for all time, right? So basically, that makes sense. But the reason we're doing this now is for a very important reason, and that reason is that imagine you have a plane wave. Imagine you have a plane wave in a conductor. Now we can write its electric field. We can write its electric field as some E, which might be complex and is also a vector. So this is a complex vector amplitude times e to the I of kz minus omega t. Okay? Let's say we have some plane wave which has just entered a metal. So what's omega? The omega is the angular frequency. We know this. Now omega is the angular frequency, and so the time period of one oscillation is equal to t, which is equal to 2 pi by omega. Okay? So now here's where things get really interesting. If this factor of 2 pi by omega, if the time period of the wave is much greater than the characteristic time tau, then charge, any free charge dissipates, and you don't need to worry about it for an electromagnetic wave. So if 2 pi by omega, which is the frequency of the electromagnetic field, is much slower than the characteristic time, which is really fast, let's say in some really good conductor, then all the free charge flows away very quickly and neutralizes. But on the other hand, if 2 pi by omega is, you can say, less than tau, if for example 2 pi by omega is approximately equal to tau, then free charge matters. For a lot of metals, at some frequencies, the charge dissipates very quickly. At other frequencies, the charge does not dissipate very quickly, and so you have to be slightly careful. And so the second case, of course, so if this is case 1 and this is case 2, so the first case would be a very good conductor. This would be a good conductor. And the second case would be an insulator, a poor conductor. Right? So we will solve the case which is the ideal case. We will solve the case where 2 pi by omega is much greater than tau. Okay? So basically we will solve for a good conductor. Okay, we'll solve for a good conductor, and in this approximation we can put rho f to be equal to 0, because any free charge automatically neutralizes. So our Maxwell equations become this is where it gets interesting. So our Maxwell equations become, well, del dot E is equal to 0, very convenient. Del dot B is once again 0. Third Maxwell equation becomes that del cross E is equal to minus partial B by partial T, once again unchanged. And the fourth Maxwell equation becomes that del cross B is equal to mu epsilon partial E by partial T plus sigma mu times the electric field. And the main thing that we've been allowed to do by putting rho f is equal to 0 is by modifying the first Maxwell equation, and this will come very handy actually. But please do make sure that you understand exactly what these, like, you understand exactly what scenarios these Maxwell equations are working for, how they're different from for the Maxwell equations for an insulator. The only difference is this factor of sigma. If you put sigma to 0 as we did for an insulator, you will recover the exact same differential equations we had for an insulator. Okay, so it's the only. So now that we have our differential equations, let's derive the wave equation. For electric and magnetic fields in a conductor. Now the starting point will be the same. So you take your third Maxwell equation, which is just that del cross E is minus partial B by partial T, and what you do to that is that you take the curl. So just like we did before, del cross E becomes equal to the divergence of rho over epsilon minus del squared E. Okay, but we've already seen that this factor is 0. So what we're left then is that minus del squared E becomes equal to minus partial by partial T of partial B by partial T. But if you substitute differential equation 4, then partial by partial T of partial B by partial T, well, we know that del cross B and how that was related to E, right? So I'll just write one more step. So this is del cross B, but then if you substitute differential equation 4, it becomes minus partial by partial T of mu epsilon partial E by partial T plus mu times the conductivity times the electric field vector. Now we can write this in a more compact form neatly as del squared E becomes equal to mu epsilon del 2E by del T squared plus mu sigma partial E by partial T. Okay, so this is our new wave equation for the electric field. Okay, so this is our wave equation for E. Notice that this is exactly like our wave equation for E that we had before. The only difference is this new factor of mu sigma partial E by partial T, which is equal to 0 if sigma is equal to 0. So this new factor is added, and if you remember, okay, when we first derived the Maxwell equations, the equations for telegraphy, this factor was already there. Okay, so let's just call this equation A for now, and let's then go to the next slide. And so by similar logic, so similarly, you can arrive at a wave equation for B, and that basically is that del squared B by the exact same chain of thought is equal to mu epsilon del 2B by del T squared plus mu sigma times partial B by partial T. Okay. So now, and let's call this equation B. So now we have our two differential equations, and the solutions to these two wave equations would be those solutions which are allowed to exist inside a conductor, right? Those waves which are inside allowed to be in a conductor. Now, it turns out that the solutions are actually very similar, and we can, in fact, we can still have plane wave solutions, right? So consider the plane wave. If you consider the plane wave, let's say E of zt being equal to some complex amplitude E naught e to the I of, let's just say k some kz minus omega t, लेकिन we leave some leeway कि k जो है वो complex भी हो सकता है, ठीक है? Let's say कि this is a plane wave, ठीक है? And then let's substitute this into equation A, ठीक है? So let's see what we get. So we get that minus k tilde square, with once again tilde denotes k, it could be a complex number in general, times E naught tilde e to the I of kz minus omega t, k tilde z minus omega t, is equal to minus mu epsilon w squared times E naught tilde e to the I of k tilde z minus omega t, ठीक है, minus, we have one more term, so it's a rather long expression, minus iota, where I is the complex number, mu sigma times E naught tilde e to the I of kz minus omega t, ठीक है? So we can basically eliminate all the exponential dependence because it's the same on all sides, and what we're left with is that yes, this is a plane wave solution if k tilde squared is equal to I times mu sigma times omega plus mu epsilon omega squared, ठीक है? So if this is indeed our propagation constant, then this plane wave solution is correct, ठीक है? So but the thing is that we have k square, ठीक है? And what we want to do is that we want to express k tilde as equal to some real k, which is the usual propagation constant, plus some complex k with an I. Sorry, there's no hat here. With an I, ठीक है? So let's find Uh, let's find the square root of k tilde square, where we know k tilde square जो है that's equal to iota times mu sigma omega plus mu epsilon omega squared. ठीक है, we have to find the square root of that. So finding the square root of exponentials, of complex numbers can be easy or can be rather tricky. This is somewhere in the middle, I'll be honest. So let's see what we can do. So if k tilde is equal, I want to write it in form of some real propagation vector plus some complex propagation vector, then the square of k tilde is equal to k plus kappa I squared, which is equal to k squared, the real part squared, plus 2k kappa I minus kappa squared. ठीक है, this is equal to k tilde square, where k tilde is a complex propagation vector. Now if we just rearrange a bit, so this means that the real part of k square minus kappa square plus 2k kappa I is equal to I mu sigma w omega plus mu epsilon omega square. ठीक है, so we can compare the real parts. So we can compare the real and imaginary parts, and if you perform that comparison, what we get is that so k squared minus kappa squared becomes equal to mu epsilon omega squared, right? That's our first equation, and at the same time 2 times k times kappa becomes equal to mu times sigma times omega. So that's equation 2. So if you substitute kappa is equal to mu sigma omega over 2k into equation 1, then if you go to the next slide, then what we basically get is that k squared, ठीक है, minus mu square sigma square omega square over 4k squared is equal to mu epsilon omega square. So if we multiply both sides by k square, what we get is that k to the power of 4 minus mu minus k square times mu epsilon omega squared is equal to mu squared sigma squared omega square over 4. ठीक है, so what we have is we have a quadratic equation for k squared. So you can just simply use our quadratic formula right, which is just minus b plus or minus square root of b square minus 4ac over 2a to solve an equation of ax squared plus bx plus c, right? So if you use this, then what we get is that k squared is equal to 1 over 2 of E, sorry, epsilon mu. I'm sorry if I call epsilon E many times in this lecture. You know I mean epsilon, which is the permittivity, the total permittivity, plus 1/2 times mu epsilon omega squared whole squared plus mu sigma omega uh, squared whole inside the square root. And if you rearrange this a bit, you get that the real part of k tilde, which is k squared, which is k uska square, so k square is equal to थोड़ा सा rearrange अगर करें mu epsilon omega squared over 2 into 1 plus sigma over epsilon omega squared whole inside the square root plus 1. ठीक है, and that's the real part. ठीक है, that's the real part. Let me just make a box around it, because we usually make boxes around things you want to make sure we understand. ठीक है, so that's the real part of k square. Now notice that we've only kept the positive square root. Of course, the quadratic equation would have given you 2 square roots. So we've only kept the positive square root, okay? Because we're just looking for right, because we are looking for a real k, right? We're looking for the real part of the propagation vector. So by a similar argument, we can find the complex part, which was kappa. So we can now substitute for kappa. So we can find that kappa squared is equal to mu epsilon omega squared over 2 whole into 1 plus sigma over epsilon omega squared. ठीक है, इस पूरी टर्म का square root, but this time with the -1. ठीक है, you can check it, you get this. So if that's and we'll draw another box around this, because this is as important as the expression before. So now we have k tilde is equal to the real part plus the complex part. We know what this is, and now we know what this is. ठीक है? So the plane wave becomes then becomes that the wave E of zt becomes equal to E tilde, we were just saying like the amplitude might also be complex, it might have some phase or stuff. So but इसलिए बस generality के लिए भी हम कह रहे हैं is e to the I of k tilde z minus omega t, but now we can expand it, and it becomes equal to e naught tilde vector e to the I of the real kz minus omega t multiplied by e to the minus kappa z. ठीक है, तो अब क्या हो रहा है यहाँ? तो जो मज़े की चीज़ है वो ये है कि you get this e to the minus kappa z multiplying your normal plane wave solution. ठीक है, so this part is exactly like your plane wave solution in a dielectric, but this part is actually a decaying exponential. So, interestingly, the electromagnetic wave decays in a conductor. And we can measure how much it decays, and we can measure what properties affects that decay. So in a distance z is equal to 1 over kappa, ठीक है, the wave decays by 1 over e, ठीक है. So देखो ना, जब 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 z कापा के इक्वल हो जाएगा तो क्या हो जाएगा. So because at z is equal to kappa, ठीक है, what you have is e to the I of the real part kz minus omega t, इसमें z kappa हो जाएगा fine, e to the minus kappa over kappa, so that's equal to e to the I of k kappa minus omega t e to the power minus 1, तो यानी कि उसका एम्पलीट्यूड जो है वो डिके कर गया, ठीक है. ज़ाहिर है यहाँ कोई ई नॉट भी मल्टीप्लाई हो रहा होगा, लेकिन वो डिके कर गया है इस फैक्टर से, ठीक है. तो दिस इज यूजुअली कॉल्ड गिवन अ नेम, एंड सो दिस डिस्टेंस z is equal to 1 over kappa, ठीक है, is defined as the skin depth. So the skin depth of a conductor is the distance it takes electromagnetic waves that have entered that medium, from one point to another, to decay by a factor of 1 by e, ठीक है. So the main take home from this is EM waves decay in metals, ठीक है, and we'll be talking about this more in subsequent lectures. Now notice that if sigma is equal to 0, then kappa is equal to 0, and the skin depth is equal to infinity, ठीक है, which is really cool if you think about it, ठीक है ना. So we define the skin depth, let's say d skin is equal to 1 by kappa, ठीक है. And so if sigma is 0, yani ki the material is not conductive, then kappa comes out to be 0, so 1 over kappa becomes infinity, so the skin depth becomes infinity, which is what you expect in something like a dielectric, where you get infinite basically propagation, right? There's no decay of the electromagnetic wave. Now the refractive index we know is the ratio of the speed of light in vacuum c over the speed of light in a medium, and this is equal to n. And we also know that the phase velocity of an electromagnetic wave is equal to the angular frequency omega over k. So if we substitute, then this is equal to c over n, so we can show that n then is equal to kc over omega, ठीक है. So that's the refractive index inside a conductor. और ये जो k है, this k is the real part, ठीक है ना, which basically जो आपके exponent of iota times kz minus omega t वाले में आता है, ठीक है. This is the real part of the refractive index. And so let's then spend a few minutes talking about polarization and phase of electromagnetic waves in a conductor. Now once again, जिस तरह हमने पहले डायलेक्ट्रिक्स में किया था, we know that del dot E is equal to 0. So this must imply that E and K are perpendicular. Similarly, we know that del dot B is equal to 0. So B and K are orthogonal to one another. ठीक है? So B and K are orthogonal and E and K are orthogonal coming from the Gauss law and del dot B. So now consider an electromagnetic wave in a conductor. ठीक है? And let's just choose a polarization. So polarized along the x-axis. ठीक है? Let's pick an electromagnetic wave polarized along the x-axis. Now the electric field E as a function of zt can be written as E naught tilde still such that it can be a complex amplitude in general, times the e to the I of the real part of kz minus omega t, e to the minus kappa z x hat. ठीक है? X hat is the polarization. So the corresponding B field becomes now how do we know the B field? Well, from the relation that del cross E is equal to partial P by partial T. So you take the cross product of this electric field and put that equal to del B by del T. So then you integrate with regards to time, and so basically what you get when you do that is that the B field as a function of zt becomes equal to k tilde, which is the complex wave vector, times over w times E naught. आप याद करो कि when we had electromagnetic waves in a dielectric, this used to be E naught over V, but V is just omega over K. लेकिन इस यहाँ K की जगह K tilde आ रहा है in general. ठीक है? तो बात वही है लेकिन थोड़ा सा फ़र्क है. Times e to the I times the real wave vector kz minus omega t, यहाँ मैं expand करके लिख रहा हूँ, dotted with e to the minus kappa z. ठीक है? अब पोलराइजेशन क्या है? अगर पोलराइजेशन आपकी इलेक्ट्रोमैग्नेटिक वेव की x हैट में है तो b की पोलराइजेशन क्या होगी? k क्रॉस x हैट. ठीक है? तो k हैट क्रॉस x हैट. लेकिन प्रोपगेशन चूंकि हमने z डायरेक्शन में लिया तो k हैट इज जस्ट z हैट. नाउ z हैट क्रॉस x हैट, ठीक है, गिव्स यू y हैट. सो b जो है एज अ फंक्शन ऑफ zt बिकम्स इक्वल टू k tilde over omega e naught tilde e to the I of kz minus omega t e to the minus kappa z y hat. ठीक है? तो interestingly, not just do the Maxwell equations tell us that E and B are perpendicular to K hat, using Faraday's law, which we've applied here, we also see once again that E and B are perpendicular to one another. So E and B are both mutually orthogonal and are both decaying functions, ठीक है, in terms of their amplitude. लेकिन एक बड़ी इंटरेस्टिंग चीज़ हुई है, if you notice, which is के B of zt is equal to k tilde over w e naught e to the I kz minus omega t e power minus kappa z y hat. ये जो k tilde है, in general this is a complex number. ठीक है? So now if you notice, and this is a very deep concept, which is that there is now a complex k hat, ठीक है, in B relative to E. ये पहले नहीं होता था जब हम डायलेक्ट्रिक्स की बात करते थे. सो देयर इज सम एडेड फेज. ठीक है, देयर इज सम एडेड फेज. ठीक है, वो कैसे है? ऐसे है कि देखिए, हमें पता है कि बी की डेफिनेशन में कोई के टिल्डा है. तो के टिल्डा एक कॉम्प्लेक्स नंबर है, एंड आई कैन राइट अ कॉम्प्लेक्स नंबर एज इक्वल टू सम एम्पलीट्यूड विच इज इट्स मॉड्यूलस. ठीक है, टाइम्स ई टू द आई फाई, where a is equal to modulus of this complex number, which is equal to square root of the real part square plus kappa square. ठीक है ना? k क्या है? k is equal to k plus iota kappa, right? तो so k is equal to a e per I phi, where a is the amplitude, and phi जो है, that's the usual definition of the phase of a complex number. That's tan inverse of kappa over k. ठीक है? So in fact b क्या है? So in fact b is equal to a over omega e to the power I phi e naught tilde e to the power minus kappa z e to the power of I times kz minus omega t y hat. ठीक है? तो ये जो फेज़ है, मतलब ये जो टर्म है, ये टर्म बेसिकली व्हाट यू हैव इज e to the power minus kappa z dotted e to the power I of kz minus omega t minus phi. So there's a relative phase difference in B with regards to E. So E and B are out of phase. So let's say if I can then express E as some E naught e to the I phi e, I can express B as some B naught e to the I phi b. Then I can write that phi e minus phi b is equal to phi, which is equal to tan inverse of kappa over k. So in a conductor, E and B are out of phase, and the relative intensity, the relative amplitude, the relative amplitude, not the intensity. So the amplitude of E over the amplitude of B is equal to A over omega. ठीक है? As you can see, so where A is the square root of, so it's mod k square plus kappa square. So pictorially then, let's look at a figure. I'll just load a figure from your textbook. So over here then we have an illustration of an electromagnetic wave in a conductor. So let's say this is the electric field. The electric field is polarized along the x-axis, जो अभी मैंने example की थी बिल्कुल वैसे ही. And this is the magnetic field, which is polarized along the y-axis. Now look के the electric field seems to be following some sort of a sinusoid, यानी कि origin पे 0, whereas the for illustration purposes the magnetic field seems to be following some sort of a cosine dependence, क्योंकि जहाँ ये 0 है वहाँ ये 0 नहीं है. ठीक है? So the E and B are out of phase, and this is representative of what happens in a conductor. And of course, the propagation is taking place in the z direction. So this is the property of electromagnetic waves in a conductor. We've seen that the E and B out of phase होते हैं. We've seen the relative magnitude, We've seen how the Maxwell equations can be rewritten for a conductor. We've seen why why the free carrier density can be set to 0. And so this is all that we wanted to discuss this time. Next time what we'll do is so next time in next lecture we'll explore skin depth a bit more, and we'll look at transmission and reflection at a conducting interface. Okay, so that's it for this time, and hopefully these concepts are clear. Okay, thank you.